So it is recording now, and this is solutions of suggested problems for chapter 9, equilibrium. And we shall start with question number 4. As you can see on the screen, question number 4 says the following. What is the mass of the diver? Diver يعني الغطاس. In the figure, if she exerts a torque of 1,800 Newton meter on the board, and he's given us the torque due to her weight. طبعا her weight acts in this point downwards, and he says that the torque of her weight about point A. Note that once he said the torque, he immediately said relative to the left A support post. You can never give torque without reference to the point about which you take rotation. You see, it is important. Whenever you calculate torque, it must be with respect to a given point, because torque changes when you change the point of rotation or about which you take rotation. So he's given us the torque due to her weight, and he wants us to find her mass. So as I taught you, always have a simple sketch. This is support A, this is support B, and this is her weight here. It's acting downwards. Now, he's given us the torque due to her weight with respect to point A. So we take torque about point A counterclockwise as positive. And probably you all know by now that mg exerts a torque. Is it counterclockwise or clockwise? This force. Imagine this is a ruler, and that ruler is fixed at point A. Now this force, is it going to be clockwise or counterclockwise?
Clockwise.
Clockwise. Good. Yes, clockwise. So that's why I had a minus sign here to show that it is it's a clockwise rotation. It's the magnitude of the force mg multiplied by the lever arm. Who can define the lever arm for me? What is the lever arm?
4 meter.
Perpendicular distance.
It is perpendicular distance between what and what?
Between the force or pivot.
Between the line of action of the force and what? The pivot. Yes, between the line of action of the force and the pivot. And he tells me in the question, this torque equals as a magnitude 1,800, and I have added the minus sign here because it's counterclockwise. So immediately the only unknown in this question is the mass, and the mass turns out to be almost 46 kilograms. Other question number 4, and it's a straightforward question. Now, question number 5 is on the same sketch. He says the following in 5. Calculate the forces FA and FB that the supports exert on the diving board. Yani there is a force on FA, there is a force at B, okay, where those forces coming from, they come from the supports, like you have two walls here, okay. So he wants us to find the forces FA and FB in two cases. The first one, ignore the weight of the board. Yani assume this board has no weight, it's massless. And in the second part, take into account the board's mass and its the board's weight, and the mass of the board is 28 kilograms. Assume the board is at the center. Okay, let me ask you this question. Now this is the board, and the board is placed on the two supports here. If you just place the board as it is, when this diver stands on it here, what do you think will happen to it? What is going to happen to this board?
Bend.
You have a force here, صح? Downwards. Now, this diver will move the board clockwise. Yani this end will move down, while this end here will move where? Is this going to stay in place or move up? Here.
Move stay in place.
ليش stay in place? Okay, fine. Suppose it is not fixed. Maybe you said it will stay in place because you think it is fixed. If it is not fixed, where is it going to go?
Up.
يعني هذا exactly up. يعني look at this. هذا هو البورد. The ruler is the board, and you have a support here, and another support here, and a force here. Okay. This force is vertically downwards like this. This is point A, this is point B, or support A and support B. Okay, and you have, this is the board. Okay, suppose this is not fixed. I just placed the board without fixing it, and I have a force mg acting downwards here. Okay, what is going to happen to this ruler? This end will go down, and this end will go where? Will go up like this. So it will lose contact with what? With this support. It loses contact. So in order to stop this, in order to stop A going, or the board at this end from going up, and we need this board to stay in place horizontal, otherwise he cannot dive. This will move all down and it will collapse. We don't want this to happen. What should we do at this point here? What should we do to the board so that it does not move up? Yes, you must fix it. ثبتها by a nail, for example, or by sticking it to the wall. Somehow you need this end of the board to be fixed to the wall, so that when it tries to move up, the wall will, or the nail which is plugged into it, will exert a force wear on it down. Okay, so that the direction of the force at point A is where? Is downwards. You see, if it is not downwards, this end will move where? Upwards, when this diver stands at the tip. واضحة هاي؟ طيب, what happens to this board here, or what happens to this point here? The board will, this end goes up, this end goes down. If this wall is not here, what happens to this point? It will move down. When this whole system collapses down, this point here, if you don't have the wall here, it will move down. So the presence of the wall stops it from moving down. So it acts with a force where? Upwards. So at point A, we have a force on the board acting downwards. We call it Fa. And on B, the force from the wall on the board acts where? Upwards. This is what I want you to really understand and realize. So the graph would look like this. The free body diagram looks like this. You have a Fa acting downwards, Fb acting upwards, and the weight of the diver acting downwards. Now, he wants us to find or calculate or determine Fa and Fb as magnitudes. So we can do the following. I have taken torque about point A. Now tell me, by taking torque about point A, which force can I calculate, Fb or Fa?
FB.
Now, Fb, yes. What is the torque of force Fa at point A?
Zero.
Now, because its line of action goes through the point, so its torque is 0. So I only have torque due to Fb and m prime times g. M prime because the weight is different from the previous example. Okay. So taking torque about point A, we have Fb multiplied by the lever arm, which is 1, and it is positive because this is a counterclockwise rotation, minus m prime times g, which is the magnitude of the force multiplied by the lever arm, which is 4 meters, which is the length of the board. All that should be equal to 0 because this is in static equilibrium. And therefore, Fb is going to be equal to 4 mg, and you get that Fb 2000, almost 2038 newtons. This is the magnitude of Fb. How can I find Fa now? What can you do to find Fa? You have two options. You can take torque about point B, so that you eliminate the torque of B around B, and you end up with only the torque of Fa and the torque of m prime phi g, so you get Fa. Or you can say that since this beam is in static equilibrium, then the sum of all forces equals to what? To 0. So you have Fb minus Fa minus m prime times g equals to what? To 0. And this ends up with Fa being equal to this magnitude. Otherwise, if you don't want to do this, just take torque about what? About point. I want to find FB. Take torque about point A, you find FB. Take torque about point B, you find what? You find FA. Whichever one you want, you can do. It's up to you. And I have given you the other way, alternative.
دكتور بالله
Now,
سؤال لو سمحت.
yeah.
دكتور هلا هون احنا بنحمل وزن البورد.
Yes, in this part, yes. He said ignore the weight of the board. Now,
Mm.
that's why in part B, you see, in part B, he tells us to take the mass of the board into account. Now he says that this board has mass, and its mass is 28 kilograms. So I must take this into account. How do I take it into account? Its weight, I have to add a third force, which is its weight, the weight of the board. Now this is a uniform board, يعني منتظم. Where does its weight act? At which point should I draw the? In the middle, yes. Yes, I draw it in the middle. Now, the full board is 4 meters in length. Okay? So it has to be in the middle. So it's 2 meters to the left and 2 meters to the right. And so I will have, from A to B, it was already 1 meter. So from B to this weight is another 1 meter. And you are left with the 2 meters on the right. And we do the same as before. If you take torque about point A, you get FB. And if you take torque about B, you get what? You get FA. So I've done it this way, and you have the solutions. Alternatively, after finding one of the forces, either FA or FB, you can say that the sum of all forces equals to what? Equals to 0. That's it. Okay.
دكتور عادي أسألك سؤال لو سمحت.
Yes.
دكتور هلا إيش نوع الفورس تبعون A و B؟ Contact forces?
Okay. At this point, yes, it's a contact force. Why? Because
It's
this,
B.
yes, point B, it's a contact force because B is in contact with the wall. True?
Okay.
Now here, it's also another contact force, but it is due to the nail. Okay? You have a nail here into the board that goes into the wall. So this is really, it's a sort of contact, it's a sum of contact force between the head of the nail and the board and the frictional force between the nail and the wall. It's the combination
دكتور
of
يعني
all. Yes.
sorry كمل دكتور.
The combination of those two forces gives you the force at point A. If you don't have a nail here, or if you don't stick it somehow to the wall, this point of the board will move up and it will lose contact with the wall. So you don't have a normal force and you don't have anything. So what do you do to keep it in place? You need to stick it somehow. You need to have nails.
Apply a force downwards.
Yes. It's like applying a force downwards.
Okay.
You can think of it as a contact force between the nail and the board, in addition to frictional force between the nail that goes into the wall. It's a combination.
لأنه دكتور أنا أول ما شفتها إنه فكرت إنه contact force between the stone and the board. فحطيتها upwards يعني هيك تخيلتها.
No, it is downwards. Yes, it's downwards.
Okay,
why is it downwards? It's important to realize why it is downwards. Because just imagine this is not fixed at all. You can do this at home. Just bring a ruler and put it on two supports. If you apply a force here, this end goes down, while this end goes where? Goes up. So you need to apply a force here downwards, okay? So that this point remains in contact with what? With the wall. You need a net force.
Okay, thank you.
Okay. Right. For question number 4. Let's see the next question. Question number 16. 16 is exactly the same idea. Let's go down to 16. Where is 16? This is 16. In 16, he's given us a beam. This is a beam. This beam rests on two supports, over here and over here. And you have 3 forces applied to the beam. It's like weights. You can think of this as a table. have two legs here that you can see, and you have two legs in the background. And you have three books, for example, on the table. You can think of it this way, but those are much larger weights than the weights of the books. So those forces act on the beam where? Downwards. And if the supports are not present, what will happen to this beam? It will move downwards. What stops it from moving downwards? There must be a force here, upwards, and another force here where? Upwards. So you have FA, FB, and the three weights. So what does he want us to calculate? Calculate FA and FB for the beam shown in the figure. The downward forces represents the weights of machinery on the beam, and these are the weights of machines. Assume the beam is uniform and has a mass of 280 kilograms. Now, he does not ignore the weight of the beam now, but he did not draw it either. So we need to draw the weight of the beam. Where should the weight of the beam act? Right in the middle. Like right in the middle. Where exactly? This is 2 meters, and 4, 6, 3, 9. So the full length of the beam is 10 meters. So where does its weight act? Right in the middle, here. It will be 5 meters to the left and 5 meters where? To the right. So you make a very simple diagram. And this is the diagram I have made. It has to be here, right in the middle. Now this is 2 meters. This is 4 meters. This is his plot. Now 2 plus 4 is 6 at this point. So I must move to the left by 1 meter, and I draw the weight. So that this is 2 meters and this is 3 meters. This is 1 meter, 3 meters and 1 meter. 1 and 3 is 4, 4 and 1 is 5. So it is, the weight is 5 meters from the right end, and at the same time 3 plus 2 is 5. It is also 5 meters from the left point. So this is the place where you should sketch your weights. And now we have FA unknown and FB unknown. Since you have two unknowns, how many equations do you need?
2.
I need 2 equations, yes. Where do I get them from? I have chosen in this example to start with sigma Fy equals to 0, which is the sum of all forces acting on the beam must be equal to 0. And as you can see, those forces only act along the y-axis. So you have Fa minus this force, minus this, minus this, minus the weight, plus Fb, all that equals to 0. And you get an equation Fa plus Fb minus 9,600 minus 280 G equals to 0. So this is one equation, and I have two unknowns. I need another equation. Where do I get it from? You can take torque about point O, for example. If you take torque about O, then which force can you find? Fa or Fb?
FB.
FB, yes. So you find FB, as you can see. This is FB. And once you find FB, you can go back to this equation and find what? And find Fa. And this is the Fa you can get. So it's straightforward application on how to calculate torque due to a collection of forces. Now we go to question number 17. And question number 17 is the seesaw question. And I have done an example on the seesaw question in the lectures, but we will do it again because there is a slightly new idea in this. Look at this. They call it the seesaw, which you see in the fairground, اللي هي مدينة الملاهي, fairground. You have two children. One has a mass of 45 kilograms on the board at the left end of the board or the beam, and the other is 35 kilograms at the right end of the beam. And now this beam, I think it has a length of 3.2 meters. And he says that this stone acts as a fulcrum. Fulcrum, you can call it a pivot, whichever you have, a fulcrum. Okay, you can call it pivot if you like. A fulcrum rock acting as pivot at the center. He tells me that it is placed at the center here. So to the left is half the length, which is 1.6 meters. And to the right, up to this point, it's half the length, which is also 1.6 meters. Now, can this beam, as drawn here, be in static equilibrium? Look at the diagram. Can this beam be in static equilibrium with this one on the left and this one on the right? Can? Is it possible?
لا.
أكيد لا. Why? صحيح, but why?
لأنه نفس الديستانس between البيفوت والبني آدم بس ماس مختلفة.
أيوة, the lever arms are the same, but this mass is greater than this mass, so this weight is greater than this weight. So in which direction is this seesaw going to rotate? Clockwise?
Counterclockwise.
أيوة, it will rotate in this direction, counterclockwise. نعم, it will go in that direction like that. يعني, in other words, the 45 kilogram boy will move down and the 35 kilogram boy will move where? Up. So this beam is really not in static equilibrium because net torque does not equal to 0. So he says, where should this little girl sit so that this becomes in static equilibrium? Now tell me, should she sit on the left-hand side or on the right-hand side?
Right.
The right-hand side, yes. Why?
تصير التورك متساوي على الجهتين.
طيب, why can't the torque be equal if she sits here?
لأن الماس تبع
but why? Note, this is the higher weight and this is a lower weight. We need an additional torque to help the lower weight. Okay? So she should sit on the side of the lighter child who has a lighter weight. So now I draw a free body diagram like this. This is the weight of the 45 kilogram boy. This is the weight of the 35 kilogram boy. The full length of the board is L, and I have written it as L over 2. Now, what is this force I have drawn here? What is this?
Normal force.
This is the normal force. Yes, it's the normal force. Now, we agreed that the girl should sit on the right-hand side, and I have suggested, as he given in the question, that the distance from the rotation point to the point of application of her weight is x. Do I know x now? No, I don't. I will find it. Like, how do I find it? The easiest way is to take torque about what? 0.0. But give me one advantage of taking torque about 0.0. What is the advantage of that?
عشان ما بنعرفش normal force.
Yes, I get rid of n. Okay, I get rid of n. Why? Because the torque of n at this point is 0. Also, if he has, also the weight of the beam will act at this point. Its torque also at this point is going to be equal to what? To 0. Okay, so I am left with the torques due to the 45G, 25G, and 35G. So, which of those forces causes counterclockwise rotation? 45, 25, or 35?
45.
Counterclockwise 45. That's it is. It's positive. 45G is the magnitude of the force multiplied by the lever arm, which is the perpendicular distance from the rotation point to the line of action of the force, which is L over 2, minus 25G multiplied by X, minus 35G multiplied by L over 2. All that equals to what? To 0. And remember, L equals 3.2 meters. So you get an equation where only X is unknown, and you get that X equals to 1/5 L, yani L over 5. Evaluate for L and you get the value of X. And X turns out to be 0.64 meters. So she should sit at a point 0.64 meters from the rotation point. Yani from this point to the rotation point, it should be 0.64 meters to the right of the pivot, close to the lighter mass. Okay. So let me ask you this question. If one of you in the exam, for example, if this was an exam question, he made a mistake. Instead of suggesting that the girl should sit on the right, next to the or close to the lighter weight, he drew the weight of the girl on the left over here, for example, and he said this is X. What do you think he will get?
يكون
راح يطلع
التورك
بالسالب.
سالب.
he will get minus 0.64. Yes, which means that x should not be on the left, it should be where? On the right. That's what it means when you get it minus. I just wanted to point your attention to this point. Now we go to question 18, and we've done a very similar question to that of 18 in the lectures, and it is about putting up a sign. This is a sign like Paul's auto repair. When you, inshallah, finish your studies and you become a doctor, the first thing you think of is having probably your own clinic. So you want people to know that there is a doctor in this building, so you have a sign. So what you do is you bring a beam. This is a beam. You attach it to the wall at this point, and you put your sign like this. And if you don't have this rope, if you don't have this rope here, what will happen to this beam?
It will fall down.
It falls down. Now, thankfully, you have done 105, and you remember, I should have a rope here. I attach the rope to the beam, and I attach it to where? To the wall, so that this beam does not fall down, and it remains in what? In static equilibrium. So he tells us in the question that this is the weight of the sign, I think 215 newtons, hangs from the end of a uniform 155 Newton beam, as in the figure. Okay, and this beam has a weight of 155 newtons, and the sign has a weight of 215 newtons, and you attach this whole system, the beam and or the beam, let's say, to a wire, and the wire or the rope is connected to the wall. Now he's asking about two things. He's asking about the tension in the wire. What is the tension in the wire? And also, he's asking about the hinge force at this point. Now, whenever you have objects in contact, you have a hinge force. But what is the hinge force due to? I told you before in the lectures, the hinge force is a sum of two forces. The normal force, because you have contact between objects, and the other force is what is due to friction. Now, if the surfaces are absolutely smooth, then you will only have normal force. But if you have rough surfaces, you have a normal force, and you have a friction force, normal force and a friction force, okay? And this what gives the hinge force. So it's a sum, vectorial sum of those two forces. طيب, how do we go about finding the value of the tension and the hinge force? Now, note in the example, he has not given me the direction of the hinge force, Mazboot. He only tells me there is a hinge here. I should know that there is a hinge force. In the lectures, he had given us then what the direction of the hinge force was, but here he does not. So what should I do? You just suggest the direction. Okay, I'll show you how to suggest your directions and to judge whether your directions are right or wrong. Now, you sketch a free body diagram. This is the weight of the sign. This is the weight of the beam. Okay, and remember the beam was 1.7 meters, and the weight of the beam must act right in the middle. So this is 0.85 and this is 0.85. The tension is attached to the beam a distance of 1.35 meters from the rotation point here. Now, if we take, now as you can see, I have sketched hx to the right and hy downwards. Now, this is only a guess. I guessed the directions to be so. So it's only a guess. طيب, how do I know if my guess is right or wrong? How do I know if I really have hx to the right or not? How do I know if I have hy downwards or not? I really don't know now. I don't know at all about hy unless I solve the question. Now, if I find that hy is positive, this means my direction is correct. طيب, if I find it negative, it means that the magnitude is fine. We take the absolute value, but the minus sign means that hy is not really downwards. Hy is where? Upwards. This is what it means, and we will see now. But for Hx, I am sure that the direction of Hx is correct. Who can tell me why? Why should Hx be to the right? It's definitely
Normal
to the right.
لأن الشد
It's another
لليسار.
thing than the normal force. Well, one way is the normal force. There is another thing. What is
الشد
it?
لليسار.
You have, look at the horizontal axis. What forces act along the horizontal axis? The component of the tension. T cosine 35 acts to the left. So in order, if this is the only force acting on the beam to the left, the whole beam will move to the left. So it is not moving to the left. The only thing that must happen is that there is a force that acts where? To the right. To oppose what? T cosine 30 and keep this beam in equilibrium. So I know Hx is correct. But I really, without solving the question, I really don't know whether Hy is up, is down, or up. Okay. As she said, you can think of this as being the normal force. You see, if this wall is only up to here, yani there is no wall here, what do you think will happen to this beam? Definitely moves like that. Okay, because there's nothing to oppose the component of the tension. Anyway, I don't know Hx, I don't know Hy, so the best thing to do is to take torque about this point so that Hx does not appear in the torque equation and Hy also does not appear because their torques about this point is zero. Why? Because their line of action, it is true that I have drew Hx here. Hx is really here and Hy is really here. So they go through the point of rotation. So their torques are zero. So if I take torque about this point, counterclockwise as positive, I get T sine 30, which is the vertical component, multiplied by the lever arm, T sine 30, multiplied by 1.35, which is the lever arm, for the vertical component. طبعا the horizontal component does no torque because it goes through 0.0, minus 155 multiplied by its lever arm, which is 0.85, which is half the length, minus 215, the weight of the sine, multiplied by its lever arm, which is 1.7, all that equals to 0. And the only unknown is the tension. And immediately you get, if you do your numbers correct, you get 642 newtons. So this is the value of the tension. Now, how do I find it, Hx and Hy? As I said, just guess a direction. Guess the directions of Hx and Hy. So sum over all forces along the x direction must be equal to 0. Hx minus t cosine 30 equals to 0. Immediately you get Hx equals to t cosine 30, which is 526 newtons. Now Hx is positive. What does this mean? It means my direction is what? Is correct. Yes, my direction is correct. That's what it means. Right. Now I go and do what I want to know what Hy is. To know what Hy is, we must say that the sum of all forces on the y direction is 0. But what are the forces in the y direction? You have Hy along the y direction. You have t sine 35 on the y direction, the weight 155, and the weight of the sine. So taking upwards as positive, you get t sine 35 minus 155 minus 215 minus Hy equals to 0. Okay. I got Hy to be minus 1.8 newtons. What does the minus sign mean? What does the minus sign mean? It means that the true direction of the Hy component is not really down, it is where? It is up. So if this is a question in the exam, he, for example, will tell you that the vertical component of the hinge force Hy is 1.8 newtons upwards. That's part A, or choice A. Choice B, 1.8 newtons downwards. Which one should I choose, A or B? He says, you got an answer of minus 1.8 newtons. And I say in the exam, the vertical component of the hinge force is 1.8 newtons upwards and B 1.8 newtons downwards. It is upwards, so you should choose what you should choose A. Now, if you need to evaluate HY in any other equation of this question, you should evaluate it as minus 1.8 newtons. Minus 1.8 newtons. Why? Because all your equations are built on the assumption that HY is where? Is downwards, while it is in fact where? Upwards. When you evaluate the minus sign, you take care of this point. So don't change the sign of HY, just use it as it is. If it is positive, evaluate it as positive. And if it's negative, evaluate it as negative. Okay, that's what you should do. Can I find the hinge force itself? Of course. Horizontal component squared plus vertical component squared under the square root. And you find the component. You find the value of H is 526 newtons. Can I find the direction? Yes. Hx is to the right, and I know Hy is upwards. I know the magnitude, and I say that tan theta equals to the vertical component opposite divided by the horizontal component, which is adjacent, and you get theta almost 0.19 degrees. So in which quadrant does it lie? It lies in the first quadrant. يعني في الربع مين؟ في الربع الأول. Now we come to the last question, which is about an outstretched arm. You see, the book has many questions on how you move your forearm, how you move your full arm. In the lectures, we did the motion of the forearm, which is this part of the hand, and the rotation point was about the elbow. Now he's talking about the full arm. Now, when you raise your full arm, when you stretch your full arm and you move it upwards, the muscle that does this, the muscle that exerts the force is the deltoid muscle, this muscle here, okay? It's the deltoid muscle. While the muscle that moves your forearm, this part only, is the biceps muscle. So in this question, it says that part A, calculate the magnitude of the force Fm, the muscle force, required of the deltoid muscle to hold up the outstretched arm shown in the figure. The total mass of the arm is 3.3 kilograms. So the mass of the arm is 3.3 kilograms. And in the figure, he tells us that it acts right at this point, which is 24 centimeters from the rotation point at what? At the shoulder here. Note that at the shoulder here, which is the joint point here, we have contact between the bones, and so we have a normal force, and we also have some small frictional force because you have at the cartilage bones moving against each other, and luckily, alhamdulillah, we have what we call the synovial fluid that decreases the frictional force. Otherwise, it will hurt us whenever we move our forearms up or down, and or stretch our arms up and down, and so on. So he wants us to find Fm, the force of the muscle, and he wants also us to find the joint force here. Look, in this example, he's given you the direction of the joint force. It's a lot easier for you. Now you know that you have a horizontal component here and you have a vertical component here. Okay, so you don't have to guess anything. Right. Let's see how to do this question. Always represent the arm as a beam. You have the weight of the arm, which is mg, acting vertically downwards. It's at a distance of 24 centimeters from the rotation point. And you have the muscle force acting at this point. This is the point where the muscle is attached to the bone. See, at this point, the muscle is attached to the bone at this point. And you have the joint force here. As I said, this joint force is due to two things: normal force and frictional force. Now, in order to find Fm, I know that this full arm is in static equilibrium. So sigma tau equals to 0 and sigma f equals to 0. If we take rotation counterclockwise as positive, we have Fm. I resolve this into two components, a vertical component and a horizontal component. The horizontal component goes through the rotation point, and you have a vertical component here, and Fm sine 15 is the vertical component, and its lever arm is 0.12 centimeters, 0.12 meters. It does counterclockwise rotation about 0.0, so it's positive. This force does clockwise rotation, so I have minus mg multiplied by its lever arm, which is 0.24, and all that equals to 0. The only unknown in this equation is the muscle force, and you get it to be about 250 newtons. Now, note this, your muscle must exert 250 newtons in order to carry only your arm, which is only almost 33 newtons. So you exert 250 newtons here by your muscles to carry what? To carry only 33 newtons. Now, what is the mechanical advantage in this case? Is it greater than 1 or less than 1? Mechanical advantage. If you remember, we said the mechanical advantage is the load force, which is what I'm carrying, mg, divided by the applied force, which is the force that applied. So it is 33 coming from m times g divided by 250. So it's almost 1/5, 1/5. So is your arm, since the mechanical advantage is much less than 1, is your arm a good lever? The answer is no. And if you don't exactly know what I mean here, go back to the last lecture and the lecture before it. I explained this extremely in a lot of details. طيب, how do I find Fj, which is the joint force? He's given me the direction of Fj. So I say that Fj has a horizontal component and what? A vertical component. And apply that sigma Fx equals to 0. And if sigma Fx equals to 0, the only forces acting along the x-axis are the horizontal force of Fj in this direction and the horizontal force of the muscle, or the component force of the muscle, which is Fm cosine 15. So I get that equal to 0, and immediately I get Fx equals to that. Along the y direction, you have the vertical component of Fj, you have the vertical component of Fm, and you have the weights. So you have Fm sine 15 minus Fj, and I called it Fjy to show that this is the y component, minus mg equals to 0. And therefore Fjy equals to 32.4 newtons. So I have Fjx and Fjy. If you square them under the square root, you get this is the value of the joint force. Note, you are only carrying almost 33 newtons, while the force that is exerted on this point here is almost 300 and how much was it? Just let me see. It is 243 newtons. It is much larger than the weight you are carrying. Now, if you are carrying something on your hand here, this force will become even larger. So we really exert a lot of forces on our joints. So you don't need to carry very heavy objects, because they really, at the long run, they hurt us. You don't need to do that. And I can also find the direction. This is Fjx, this is Fjy, and I can say that tan at this angle, which is an acute angle, is the absolute magnitude of the opposite, which is Fjy, divided by the adjacent, which is Fjx, and I get alpha almost 7.6 degrees. Now I want theta. Theta is the angle with the positive x-axis in a counterclockwise direction, so this should be theta. I say that it is 360, which is the full angle, minus alpha. and I get 352.4 degrees. Okay, so those are all the questions in the suggested problems. Any questions?